My name is Tamara. I'm from CeADAR at TU Dublin, and I'm going to present our demonstrator KnowText, knowledge graphs for semantic enrichment of text corpora. Automatic building of knowledge graphs from text is a long-standing goal in artificial intelligence research. This is because knowledge graphs extract information from text, capturing relationships between entities in a network structure of entities and relationships where entities become nodes and relationships become edges. An essential part of knowledge graphs is the knowledge base, which enables automatic reasoning, meaning the ability to infer unobserved facts from observed evidence, and to also make logical steps to render data into graph analysis. Traditionally, knowledge bases are built as a relational schema using expert knowledge from ontologies or from semi-structured or unstructured text extraction. A knowledge graph consists of two layers: a knowledge base, which stores a domain's data as entities and relationships using a domain
Tamara?
ontology schema. Yes?
The screen is not full, just to highlight. Pardon me.
Okay, can you see it clearly? Hello?
Kindly make it full screen if possible.
I prefer not to because I'm not sure how
Okay,
I will
carry on.
share
No
later.
problem.
Yeah, no, that's
No problem.
absolutely fine. Don't worry.
So a knowledge base stores domain data as entities and relationships using a domain ontology schema, and a reasoning engine supports data integration from multiple sources, data query from the graph, and data inference. To look at the background of this field, we can see that there's been a lot of development of very large industrial knowledge graphs, which have been generated to enable machine understanding of semantics in the context of the semantic web. So there are many examples of industrial knowledge graphs. You may have used some of them, whether you didn't know it while using Google searches. Among these, Google Knowledge Graph, Yago, ConceptNet, and DBpedia. They're all mapping billions of entities from knowledge bases which have been created by a group of experts like Coordinate, through semi-automatic and collaboratively work Wikidata and Freebase, or auto-populated using semi-structured resources like Facebook and Wikipedia. What is common about these knowledge graphs, they all share a structured, they all have a structured knowledge base, which is strongly typed, meaning that it is annotated by experts. Other more novel knowledge graphs like NEL and Knowledge Vault develop their own custom knowledge base, which is made by fact extraction from unstructured resources. The problems for user-specific applications here are that large knowledge graphs do not allow for customization. It is difficult to extract specific custom information from large pools of data, which requires expertise, and also the query can be time-consuming, complex, or expensive. Therefore, there is a need to enable fast customization, like easy access, choices of user-defined domains, easy built and deployed such knowledge graphs, user-oriented, which all require predefined design as graph structure or reasoner. For this task, new ideas came up as frameworks for knowledge graph generation. Examples would be SMTK and YES, which are based on triple stores and external data mapping. And other examples are Kraken AI and Neo4j, which are ontology reasoner systems designed as graph databases. The query language in this case is not Spark, which is usually used in industrial knowledge graphs, but it is specific for each type of framework. Therefore, even these frameworks require user expertise for setup of a specific domain and query. There is therefore a market need for developing automated knowledge graph extraction. This is because there is a strong information overload in terms of unstructured text. Companies need to find the facts in all these swaps of data, and knowledge graphs provide semantics. Therefore, we are trying to provide solutions which customize for use case and domain, and now enable easy query methods based on natural language text or visualizations. There are very many use cases for knowledge graphs, among which data governance and integration, investing strategies like thematic investing, knowing the company's strengths and lows, marketing recommender systems and customer 360 know your customer applications for e-commerce, compliance in the field of laws and regulations, where we need to understand how these are overlapping on or interrelating with each other, and also in the field of HR. The scope of our demonstrator is to limit somewhat these very wide scopes, but still provide the main uses in an innovative way. So basically, we need to understand the text content. What are the facts? We need to enrich knowledge extracted from text data sets by expanding the knowledge representation to a wider corpus. For example, if we have a number of recent documents in the company and we want to view these in the context of previously existing documents, we can analyze all this data in the same time and extract relationships between entities found in this all common pool of text. We also need to visualize connections between entities, therefore the links, to filter the information based on the type of link or entity, and to enable further query based on text. Our technology solution, the KnowText demonstrator, is an interactive web application that enables automated generation of knowledge graphs from text collections. This involves dynamic extraction of facts from text as subject, predicate, and object triples, and dynamic generation of an OWL type ontology, web ontology, language type ontology, linked to these facts. And we can see that we can open the ontology in the Protégé editor, and we can further analyze and add features to it. And the structure of the ontology is of RDF type. The methods we have used, first, to extract triples, we need to do POS tagging, for which we used Spacey, the platform, well-known platform Spacey. We used also an ATK. We go to perform coreference resolution using neural coref package from Spacey as well. We perform dependency parsing to find syntactic tags, subject, predicate, and object, for which we use OpenIE. And we extract triples after the refinement and filtering from the pool of triples that are extracted by OpenIE to bring them into our context. To generate the ontology, we extract named entities using Spacey and NLP, of course. We extract domain-specific vocabulary, where such words would be words that appear as subjects in triples but are not in the list of named entities. The named entities we extract consist of a number of categories of such named entities as person, nationalities or political groups, buildings, airports, highways, organizations, GPs, locations, products, events, works of art, law, so on and so forth. Further on, we define classes, attributes, and instances to create an ontology. Then we assign instances to classes, attributes dynamically using our ready-to package in Python. So therefore, we populate the ontology dynamically as well. The workflow consists in a backend where all these computations, calculations are performed. So once the text is uploaded by the user, in the background, these codes are performing triple extraction the ontology is generated, the entity linking is performed, then the knowledge graph is generated, and the entity network, which will be displayed on the user interface on the front end, where the user can interact with visualizations, see the facts, the named entities, the links, and query the details in the ontology, or also filter the views, the classes, and relations. Also, the user will be able to download the files for triples and the file for ontology. So the functionality is obvious. We provide interactive visualizations of the knowledge graph. So facts extracted from text, which are the actual triples, are represented as a graph. We extract the ontology automatically linked to the extracted triples. And there are several easy ways to query the knowledge graph. For example, by selecting entities and or relations as words, by choosing them from a drop-down list, by typing in natural language text, the user has this opportunity, by viewing the facts stored in the ontology for each entity, namely the subject, as text output, and then the possibility to download the triples and the ontology file. This functionality is clearly summarized in one of the tabs, visualization tab in the app. We can see the collection name, the drop-down list of subjects, the drop-down list of predicates. We can see the network generated, the graph generated, where the size of the node is proportional to the number of links each node has. The colors are mapped to the classes in the ontology. We have a slider where we can set a threshold for the number of links for the nodes which are going to be presented to the user, so we can refine the visualization. And we can also type in text in a text box. I will conclude by enumerating the advantages of KnowText. Firstly, KnowText has high specificity, which is the fact that it will work with text in a company domain of interest, because unlike the large industrial knowledge graphs, KnowText restricts the information pool, therefore the knowledge base, to the representative data uploaded by the user. Also, the KnowText demonstrator performs automated knowledge graph extraction from unstructured text collections, allows for easy query methods based on visualization and free text. It is a web application accessible through a web link, which is built using the Django and Python framework. And it is a portable, flexible, and scalable approach being based on Python. And it is also easy to use even by non-expert users. Okay, so now I will try to present the app itself. I'll make a new share now. Can you see the screen for sharing? Hello?
Yes, we can see it.
Yes, thank you. So we log in the application, and we are going to be presented with the KnowText homepage, which has the description and the short disclaimer and a little image, which will soon be replaced by a movie explaining and providing a tutorial for how to use this application. To upload the data file, we press on the upload button and we can upload a file. Here I'm going to upload 50 text from a collection of text from financial economic news dataset. And we are presented with the table with all columns. We can select up to 3 fields as identifier. I'm going to select just one. We can select up to 3 fields for the text to be analyzed. Again, I'm going to just select one. We can choose a collection. The collection is the actual collection of documents which can include previously analyzed documents to which we can add a document. Here we can choose, for example, collection number 10. When we press on create graph, in the background, the calculations are being performed, and for this particular text data set, we would probably need around 2 minutes. I'm going to go directly into the visualization tab. And once computation has been performed, I am choosing this collection to be visualized. And the spinner will take, again, a little time to perform the display. And we are shown a graph where, as I explained before, the nodes represent various entities. For example, vocabulary appears in blue, vocabulary words, investors, dollar, interest rates, persons. We can filter the graph up and down. I will go down to show more nodes. We can choose a subject from the list of subjects, for example, Americans. And we can see how links are being displayed and how information from the ontology is being displayed. It is a class knob. So we can see how this word is connected to other words in the text. We can see, let's choose a person, for example, child list. We can see all the facts related to child list. We can see how these facts are stored in the ontology. We can reset these searches and we can look at the predicate. For example, I will look for a specific one which is very clear to see. For example, join. So we can see nodes that are all related through or by the same relationship, the same predicate join. If we choose is, for example, we'll find all the nodes that are related by the word is, or the predicate is, and this can give a view of what we can do with these searches. Again, if we reset and we type in some text, for example, it can be a free text like what Anne said. It doesn't have to have a grammatical structure. It's let's make this capital. We can launch the query and we can see that both words Anne and said have been found in the text collection. We have found a person, Anne Clemency, who tells something 2 times. We have used a similarity for finding all the possible variants of the word said. So tells, it's another one. If we press on the highlighted name, we can find all the other facts related to Anne Clemency. And we can also press on the predicate and we are going to be shown all the nodes that are linked by such word said and its synonyms. I will reset here. We also have a tutorial which can be seen online. And we invite you to visit our application and send us your questions. Thank you for your attention.